Okay, communality. Communalities are the proportion of variance of a scale accounted for by a particular subset of factors. This is not included in the initial factor analysis because all of the communalities for the initial analysis are 1.0, i.e. there is no subset, the entire set is used. This is because all possible variance is accounted for as a result of having as many factors as you do items or scales. As you might remember, the point of factor analysis is to reduce a number of items into a smaller set of more meaningful units. For example, the sum of squares of the factor loadings for scale A is 1.00, 0.92 squared, etc., all the way through, and then sum negative 0.30 squared, and that equals 1.00. Use this analysis to determine how many factors to keep for the final analysis. A scree plot. These are also used to determine the number of factors to keep for final analysis. So you have a figure 6.2 scree plot showing distinct elbow. Okay, that's a page 98, and it looks like this. Apologize. Hopefully you'll be able to orient yourself to that. And then a scree plot without a distinct elbow. And then I think with the understanding of how you look for an elbow in the data in the form of the graph shape, and the other distinct kind of elbow. And I'll put that up real quick so you can see the arrow points. Top right, if you're going to keep a particular factor for your final factor analysis, so you're going to do more than as final leads to. So the fourth step is to repeat the factor analysis using only those factors that have an eigenvalue of greater than 1, or as close as you can see by table 6.3. So if you refer to your table 6.3 that we had up earlier, excuse me, that's there right on the screen right now. I'll try to get that a little more focused. So you see proportion of variance at the bottom there. It's going to tell you the factor loadings for each of the scales. Now you notice there's 10 scale, only 4 factor loadings. So essentially the decision was 4 factors, and then the h squared, the values on the far right, refer to the communality. The only difference in 6.2 and 6.3 is the inclusion of the communalities and the exclusion of factors 5 through 10. To repeat, the communalities are a representation of how much scale or item variance accounted for by the subset of factors. For example, 0.92 squared all the way through to 0.05 squared equals 0.88. So essentially 88% of the variance is accounted for by those 4 factors. So the remaining 6 factors only would account for, in theory, and hopefully the way the math would work out, 12%, or 0.12. Basically meaning that they're not of much utility when it comes to using these tools, these 10 scales, to assess or to somehow get at whatever this factor is that we're going to name or interpret, which is the 5th step, interpreting factors. Further research needed to confirm interpretation of factors and there is extreme subjectivity in interpretation of factors. It's what makes horse races and also what makes different areas of psychology. So in many respects, we all do the same types of studies. We do steps 1 through 4 across the disciplines of psychology very similarly. It tends to be the interpretation that is the biggest variability, and that makes the horse races in psychology, or the different fields, as well as the data that is used in the analysis and the assumptions, basic assumptions, what kind of science you are, which we got to in our Q sort. So hopefully you're seeing a common thread between Q methodology, generalizability theory, and factor analysis, and then a big thread through them all, which is essentially correlated. The issue of rotation. Burstone in 1947 proposed that factors should be rotated to simple structure, defined essentially as the attainment of factors with mainly nil loadings, but with high loadings on the remaining few variables. The law of parsimony guides this suggestion. It has been well received by people that use factor analysis the most. Each factor is rotated such that it is related, but highly, to a few variables, scales, or items. The assumption is that simple structure will be obtained by maximizing the zero loadings on factors. So you want something to load high but on a particular factor, but also load low on the other factors that you use in your final factor analysis. Two types of rotation, as I mentioned earlier, orthogonal and oblique. In order to obtain higher order factors, which we won't get into during this presentation, you must use oblique rotation. This is necessary because factors must be correlated with each other, since higher order factors are broader in scope and encompass lower order factors. Orthogonal rotation. Baramax rotation is the rotation of choice under the orthogonal rotation type. Orthogonal factors, because of their statistical independence, factors are not correlated, possess the simplicity and elegance that oblique factors do not. It is important to note in rotation that although the factor matrix changes, the communalities and the percentage of total variance explained do not change. However, the percentage of variance accounted for by each of the factors does change. So an example of an orthogonal rotation is overhead 7.13a through 7.13d. As you look through these, notice the change in factor loadings, but if you sum the square of all loadings, the amount of variance accounted for remains the same in each of the examples. Thank you.